4.5 is stoichiometry. So our outcome is I can explain changes in the amounts of reactants and products based on the balanced chemical equation for a chemical process. So stoichiometry explores the quantities of reactants and products that are involved in chemical reactions. The coefficients in a balanced chemical equation indicate the number of molecules or formula units, and they also indicate the number of moles involved in a reaction. So these coefficients are proportional to each other, and they can be used to convert from moles of one thing to moles of a different thing in a chemical reaction. So stoichiometry is just that. It's going from moles of one substance to moles of a different substance that are related by a chemical equation. So we use a mole ratio to convert from moles of one thing to moles of another thing. Other than that, everything else is just a matter of using a conversion factor to convert the answer or the given into the desired units. So we can convert between grams and moles using molar mass, particles and moles using Avogadro's number. And particles is a generic term. It could be ions or molecules or atoms or whatever. We can use molar volume, 22.4 liters per 1 mole of gas. That is only for gases. It is not for solutions. If we want to use solutions, then we need to think about molarity, which has units of moles per liter. So the first equation here that we have to balance is the thermite reaction. So the first question says, what masses of Fe2O3 and aluminum must be used to produce 15 grams of iron? So I'm going to do two calculations here, one for each reactant. So I'm going to start with my desired amount of iron, which in this case is 15 grams. Then I can convert that into moles of iron, and then I can use this mole ratio to convert to moles of iron 3 oxide. Then I'm just going to use my molar mass and convert it into grams of each reactant. So slightly different mole ratio and different molar masses here. This gives us how much of each of these we need. So how much aluminum oxide could also be produced? So you could grab any of the numbers that you just calculated, or you could just start again with the 15 grams of iron, which is what I did. So I'm going to convert my grams of iron into moles, mole ratio to get aluminum oxide, molar mass to get grams. Question 3, we have some lead nitrate reacting with sodium iodide, and we're going to form lead iodide solid here and some aqueous sodium nitrate. So in the first question, I want to know how many grams of lead 2 iodide can I make if I react 25 milliliters of 2 molar sodium iodide. So this is saying, assuming we have enough lead nitrate, how much lead 2 iodide can I make from this amount of sodium iodide? So first I'm going to take the milliliters of my solution and I'm going to multiply that by the molarity. So 2 moles per 1,000 milliliters is the same thing as 2 moles per liter, which is the same thing as molarity. So that capital M means moles per liter. So you can just use this as a conversion factor between the volume of solution and moles of the solute. Next, I use a mole ratio to convert to moles of lead iodide, and then use the molar mass to get grams of lead iodide. In B, I want to know what volume of this lead nitrate solution would I need to completely react with this sodium iodide solution. So I'm going to start by using my molarity and volume to convert into moles of sodium iodide. Then I can do a mole ratio, and this will give me moles of lead nitrate. Now I want to get milliliters here. So I'm going to use the molarity of the lead nitrate solution, which is 1.25 moles per liter. I can just flip that. It's still the same conversion factor, but I'm going to put liters on top. So what's going to happen here is the liters here will cancel liters here, which is why I left this answer, or rather this start here in milliliters because I wanted to get milliliters for my answer. What's the molarity of 20 milliliters of sodium iodide that reacts completely with 60 milliliters of 0.750 molar lead-2 nitrate solution? So I'm going to first convert into moles of my lead-2 nitrate solution here by multiplying my volume by the molarity. So when I do that, that gets me moles of lead nitrate, use a mole ratio, and then if I divide by my volume here, the 20 milliliters cancels out with 60 milliliters, so the only thing we're left with is moles of NaI per liter, which is molarity. So the limiting reactant is the reactant that gets completely consumed in the chemical reaction. It is going to limit the amount of product that can be formed. So some of the excess reactant is left unreacted when the limiting reactant is completely consumed. If there is no limiting reactant, or they're both limiting, they get completely consumed, it's called a stoichiometric mixture. Percent yield is used to describe how much of the expected product did we actually get. So to find the percent yield, we're going to use the actual yield, which is what we get from our experiment, divided by the theoretical yield, which is based on the stoichiometry of the reaction and the starting amounts of reactants. So for question 4 here, looking at our limiting reactant, we have oxygen reacting with nitrogen monoxide to produce nitrogen dioxide. And we also have a couple of O2 molecules left over. So this is telling me that NO must be my limiting reactant because it was completely consumed during the reaction. So I need to go ahead and balance this equation. I forgot to do that. So if I put a 2 here, that's going to give me 4 oxygens. I have 2 here and 1 here, so a 2 in front of this guy is going to give me a balanced equation. So question 5, DDT is an insecticide that is harmful to fish, birds, and humans. It is produced by the following reaction. So we react chlorobenzene with chloral to form DDT. So the first question is asking, if I start with 1,142 grams of chlorobenzene and 485 grams of chloral, how much of my DDT, my product, can be made? So this is a limiting reactant problem. I'm going to need to do 2 calculations. So I'm going to start with my given amount of chlorobenzene and my given amount of chloral, and I'm going to use the molar mass of those 2 compounds to convert them into moles. Next, I need a mole ratio to convert from moles of chloral or chlorobenzene into moles of DDT. And then finally, I multiply by the molar mass here to get grams of DDT. So the maximum amount that I can produce is 1,165 grams because chloral is going to be my limiting reactant. We're going to run out of that. So I'm going to have some excess chlorobenzene left behind in my reaction mixture. So how much of that excess is going to be left over? So I'm going to calculate, in order to produce this 1,165 grams of DDT, how many grams of chlorobenzene do I need to do that? So I started with the mass of DDT I could produce, converted that into moles using molar mass, and then converted it into moles of chlorobenzene using my mole ratio, and multiplied by the molar mass to get grams. So I started with this amount of chlorobenzene, and I'm going to use this amount. So that means I'm going to have 402 grams of chlorobenzene left over. So if the actual yield is 200 grams, so if a scientist goes and does this experiment and they get 200 grams, their percent yield is found by taking what they got by what they should have gotten times 100%. So we see we have a very low percent yield in this problem. So on the multiple choice section of the AP chemistry exam, traditionally you are not allowed a calculator. So there will be stoichiometry questions, and there will be limiting reactant questions, but they're going to often have these nice round numbers that you can easily manipulate. So you're going to need to be able to solve this without a calculator. You should still write out your work. You're not being not allowed a pencil and paper. You're not allowed a calculator. So for my first question here, we have 56 kilograms of carbon monoxide and 6 kilograms of hydrogen. I want to know how many moles of my product, which is methanol, can be produced. So I'm just going to convert my grams of CO into moles. I'm going to leave the kilo there. I don't need to worry about that, because all of my answers are some number times 10 to the 3, so they're all in moles here anyway. So then I just need to use a mole ratio to get into moles of my ethanol, or my methanol rather. So 56 divided by 28 is 2. So I'm going to get 2 kilomoles of alcohol from my 56 grams of carbon monoxide, and the molar mass of hydrogen is 2, so I have 3 moles of hydrogen, which translates into 3 moles of my methanol. So my limiting reactant is going to be the carbon monoxide, and I'm going to be able to make 2 times 10 to the 3 moles, or 2 kilomoles of methanol. In question 7, a student conducts an experiment to determine the molarity of a sodium chromate solution by precipitating it out with lead. So the student filters and dries the precipitate, and we get the data below. So I know that I've collected 1.94 grams of my compound here. So I know that just by subtracting 80.8 from 22.84, but it's 2.74, so it's 1.94. Now I gave the molar mass as 194. That was a mistake on my part, but for the purposes of this problem, use what I gave you, because this is supposed to be mental math here. So I've got 1.94 divided by 194. So that's going to be 1/100th. So I get 0.01. And then whenever I divide by 0.01 from the 10 milliliters, that gives me 1 molar of this sodium chromate solution. So why in this reaction below is it appropriate to say all these different things? So each of those is giving me the same ratio of atoms, just written with different units. They all reflect the stoichiometry of the equation. Here's 2 more equations. We have the ideal gas law, which allows us to solve for moles of gas, and then we can use that in stoichiometry calculations. We can also use the molarity equation to solve for moles. So this time it would give us the number of moles in a given volume of solution at a given concentration.